Welcome to my first Jamboard for chemical science. Technically, this is not a Jamboard, which is a Google option, but I love the term, so I'm deciding to use it. The goal here is for each one of our classroom meets to replace one of our live meets with one of these recorded ones, and that should solve some problems and give you the chance to watch it a couple times if you want. So there are 4 pages here of notes, and I'd like to make this less than 10 minutes, but we'll see how it goes. So the first page has really connection to physics class last year. So what we're going to find in this new unit on energy of reactions, we're talking about chemical potential energy and chemical kinetic energy, if you will. Chemical kinetic energy, the motion of particles, we actually measure with a thermometer. Chemical potential energy is related to energy stored in the bonds. But what we're looking at here is something from physics last year, where you would have put a cart at the top of a ramp and we would have acknowledged that there was a mechanical potential energy there. We would have let the cart go and it would have started moving. And at the bottom of the ramp, it would have had much less potential energy, and it would have had some of that energy that would have changed form into kinetic energy. So we're going to do the same thing in chemistry this year. We just don't get to see it as readily as the cart going down the ramp. These next images come from your book. So for tonight, I'm going to have you read a few pages from your book. What you can see here is these are drawn a little differently from how we often do them in class. So these oxygen here, let me just put a pen around those. This oxygen molecule here, you can see that they have the atoms overlapping a little bit. What we would have done recently is we would have drawn an atom and connected them like that, not having them space filling each other and not having them overlapping. But here they're just drawing it like this. The reaction itself should be somewhat familiar. It's taking methane, which is a carbon surrounded by 4 hydrogen, reacting it with oxygen gas to make carbon dioxide and water. That reaction happens to release a lot of energy, which is why they have energy written right there. So what we see in chemical reactions is what we get to observe is changes in the temperature of the reaction vessel, either measured by a thermometer or by our holding the reaction vessel. And so those are the observations that we make of a chemical reaction, and then we deduce what's happened to the chemical potential energy. And what we're going to learn is if the chemical potential energy, that is the energy stored in the bonds that we really can't directly measure, but if the chemical potential energy decreases as the bonds are broken from the reactants and forming bonds of the products, if that potential energy decreases, then we feel that as warmth of a reaction. And I guess let's start with that because that's what this focuses on. So again, you're going to be reading about this tonight. I don't need to go in great detail, but you're going to be learning about how what we detect is we detect the thermal energy associated with chemical reactions. Okay, so let's move this up a little bit. Oops, maybe it's on another page. Okay, so again, these images come from your book. What you learn in the reading is that anytime you separate atoms, or anytime atoms are separated, that actually requires energy. You can imagine these atoms here, or really anytime we have 2 atoms bonded together, there's an attraction there. There's a bond, and so if you're going to separate that bond, that requires energy to be added. However, then down in step 2, we're making new bonds. New bonds are forming. And it's perhaps a little less intuitive in this step 2, but anytime you 2 atoms bond, there's a release of energy. So any reaction is a 2-step process, pulling apart the atoms as they exist in the reactants and forming new bonds as the products are formed. So it's 2 steps. Let's see here. I think we might be on to page 3. Okay, so this graph here is the beginnings of what we're going to do quite a bit of. And let me mark this up a little bit. So the y-axis is labeled chemical potential energy. And on the x-axis, we're going to call our graphs reaction process. I'm going to write right over this. I don't know how well it will come out. Reaction progress. So this is going to become a familiar graph for us. And what your book does is it actually presents a lot more detail than what we would be used to seeing. But we would start with a horizontal line, somewhat arbitrarily placed, and we would recognize that as the chemical potential energy of the reactants. And this diagram here is showing us how energy gets added. That's why there's an upward arrow. Energy gets added to break bonds. You can see all these atoms are now have been separated. And so then when new bonds form, energy is released. So there's a downward arrow there. And we end up with another line at a value. There's no numbers here. It's just high and low. But we can see that the horizontal line for the products is now lower than the horizontal line for the reactants. And so, changing colors a little bit, a lot of our graphs just have this line and this line, and we make conclusions from that. So we're not always drawing the up arrow and the down arrow associated with the separating atoms, the breaking of bonds, and then the new bonds forming. Oftentimes we're just looking here and making conclusions from it. So this is a graph of potential energy, and as you will learn about in your reading, if you have a reaction in which your chemical potential energy lowers, which is what you see going from left to right, because this green bar on the right is lower than the green bar on the left. So we have a lowering of chemical potential energy, and how we observe that is that we then feel that energy being released. So if we're touching the side of the reaction vessel, wow, our hands get warm. If we have a thermometer inside the reaction vessel, that those chemicals themselves, the temperature recorded by the thermometer, it warms, because this part that we can't see, the chemical potential energy, has lowered. So to repeat that, the lowering of the chemical potential energy means an increase in the kinetic energy, just like the cart going down the ramp. How do we measure molecular kinetic energy, if you will, the particles moving around? That's with a thermometer. Okay, once again, I've got to emphasize that you'll be reading about this in your text. So this may sound fast. You're welcome to replay the video, but these concepts will come over time. Okay, so we've got what would hope to just be a couple minutes left here. And now what I've got is I've got some images here that I made that we're likely to see a lot of. And so what I want to do on these is just mark the two horizontal bars, much like you saw me do in green up above. And so the first time I do this, and I'm really removing a lot of the detail that your book provided. Here, this is a chemical potential energy versus reaction progress, just like we wrote up above. But we're focusing just on a horizontal line for the reactants and where the corresponding horizontal line is for the products. If we have what's called an exothermic reaction, such as an explosion, that means, wow, we felt warmth. We felt a pressure wave, we felt warmth, we felt the energy coming out of the system. Well, if we made that observation that energy came out of the system, that means that chemical potential energy lowered during that reaction. There's the products. And so this is analogous to the cart going down the ramp, right? The potential energy drops and the kinetic energy increases, which we feel is the warmth in the thermometer reading going up. That means the potential energy was dropping. Interestingly, in chemistry, we have to be prepared for the flip of that, and that is when chemical potential energy increases. Chemists call this an endothermic reaction. We're not answering the question of why this would occur. We just need to be prepared for the possibility that happens. And so if you go from reactants to products, and the products are actually storing more potential energy than the reactants, well, that required energy to do that. This is an uphill climb, if you will, for the chemical potential energy. How does it do that? It takes energy from us. We feel cold. We watch the thermometer in our reaction vessel decrease. That drop in temperature, that drop in the motion of the particles, taking that energy away from it is what drives the chemical potential energy up. All right, I'm over 10 minutes. I'm just curious what I had on the last page, which I won't talk about here. Okay, I won't talk about that. We're going to leave it for some of you reading and perhaps for another day. Thank you.